Hello students, this video is for the 4th unit. We're talking about lesson 5, which is rotational and line symmetry. We've talked a little bit about how to take shapes and transform them, and now we're going to be talking about how to identify transformations that'll make them symmetrical. Specifically rotational symmetry, which is spinning a shape so that it appears to be the same, and then line symmetry, which means we can fold it over a line that we can draw through it, which ends up looking the same. Let's take a look at the learning target. I can use rules of rotational symmetry and line symmetry. We're going to be talking about those rules during the lesson to identify map onto transformations. Now, the idea behind map onto transformations, we want to make sure that it looks the same after the transformation. So we might say that the transformation maps a shape onto itself. That's what we're talking about with that. For the do now, it asks us what line of reflection would map AD onto BC. So AD is this line segment here, which I'll highlight, and BC is this line segment over here. The next question asks us what line of reflection would turn point C into point A. Of course, this is point C down here, and this is point A. And then last but not least, how many degrees would you have to rotate to map BC onto DC? So turning BC, which is this blue line here, onto DC, which is over here. Let's make that purple. Why not? All right, pause the video and try this one out yourself. All right, for that first question, what line of reflection maps AD onto BC? You can see that I drew it in here. AD and BC are equidistant from this dotted line that I just drew in. In other words, A is the same distance away from this line as B is. D is the same distance away from the line as C is. So I would call this a line of reflection. We talked about lines of reflection during one of the previous lessons, which was about reflection. So anyway, we call this line of reflection line FH. And similarly, we can identify that the line of reflection that turns point C into point A is line BD. You can see I drew in BD here. It's that dotted line. And you can see that A and C are equidistant from that line. If I go along here to A and if I go along here to C, it's the same distance away. So that's how we can tell that it's a line of reflection. Now, for the third question, it asks how many degrees would you have to rotate to map BC onto DC? And what is the center of rotation? Be careful, because as you remember, rotations, if we don't specify, have to be counterclockwise. All right, hopefully this makes sense. We're taking BC and rotating it counterclockwise around point I. We do have to rotate it 1, 2, 3 times. So we're talking about 90, 180, 270 degrees. Many students in the past have said that this is only a 90-degree rotation, but be careful. We always talk about rotations in terms of counterclockwise, unless the problem specifically states it. As a reminder of the different types of regular polygons, of course, regular means that it has all the same size sides and all the same size angles. All of these shapes are considered regular. So this is a regular triangle, a regular quadrilateral, a regular pentagon, a regular hexagon, and so on. We're going to be talking about all the different types of polygons in a future unit. One thing that you should know is that there aren't any special names for regular pentagons or regular hexagons, but there are special names for regular triangles and regular quadrilaterals. You probably already know them. We don't usually call them regular triangles, we call them equilateral triangles. And similarly, we don't usually call a regular quadrilateral by that name, we call it a square. Moving on to line symmetry and rotational symmetry. So we say that a shape has line symmetry if it can be divided by a line, one of these dotted lines for example, into two parts that are mirror images. So in other words, one half is the reflection of the other half. So just taking one of these for example, let's say we're talking about this triangle. It has 3 lines of symmetry. So if we draw in this dotted line, you can see that the left-hand side is the reflection of that right-hand side. Any way that we draw this dotted line, it's going to look like that. Now this works with equilateral triangles, it works with squares, it works with pentagons, hexagons, and so on. It also works with other non-regular shapes, but it doesn't work with every non-regular shape. For example, here, let me draw you one as an example. Judging by this shape, which is a triangle, but it's not an equilateral triangle, if I were to try to draw a line of symmetry like this, it wouldn't be a line of symmetry because one half isn't the reflection of the other half. And even if I try to move this over a bit, maybe I try to move it over here, it's still not a reflection of the other half. So it looks like this shape, this particular triangle, does not have a line of reflection. So in other words, it doesn't have line symmetry. So some shapes have line symmetry and some don't. Moving on to rotational symmetry, which is spinning around, We say that a shape has rotational symmetry if it can be rotated around its central point by some number of degrees. So for example, I'm looking at this hexagon. I could take its central point here and then say, well, I'm spinning this shape around its central point. And you can see in this particular example, it is rotating around clockwise, but counterclockwise is also a valid way to identify rotational symmetry. And anyway, rotate it around its central point by some number of degrees and be identical to the pre-image after that rotation. So we're talking about the pre-image and the image. In other words, the shape is said to be rotated onto itself. Or another way to say it is mapped onto itself. And this is a key phrase. If you ever see the words onto itself, that means the question is talking either about line symmetry or about rotational symmetry. Onto itself is a dead giveaway. The last thing that I have on this page is about minimum degree of rotation, which means if I'm taking this shape and I'm trying to spin it around so it maps onto itself, I could spin it around 360 degrees and it'll easily map onto itself. However, there are smaller numbers of degrees that I could spin it so that it maps onto itself. In order to find the smallest degree of rotation, in other words, the smallest angle that I could spin it around, I need to identify the number of sides it has. If it's an n-sided regular polygon, for example, in this case it has 6 sides, we say the minimum degree of rotation is an angle, and that's equal to 360 divided by n, which is the number of sides. So in this case, the minimum degree of rotation, in other words, the smallest angle that I could spin it so that it maps onto itself, is equal to 360 divided by 6, because there's 6 sides here. 360 divided by 6 is 60. That's why I have 60 written here, because the minimum degree of rotation of a regular hexagon is 60. Notice I have another triangle here that is not a regular triangle. It's not an equilateral triangle. And if I try to spin this around its center, first of all, trying to find its center is not really easy. And second of all, if I spin it, there's no way that I'm going to map it onto itself, unless, in fact, I spin it all the way around 360 degrees. Every single shape that you could possibly think of has 360 degree rotational symmetry, so we don't really consider that to be a type of rotational symmetry. We're only considering rotational symmetry if we can rotate it a degree smaller than 360 to make it map onto itself. So as an example, I've traced out this hexagon, and what I can do is, instead of rotating it all the way around 360 degrees, I can show you, well, only rotating it 60 degrees is going to map it onto itself. See, it completely covers up the original shape. Same thing here. So I've done 60. Here's another 60, which is 120, and you can see the black dot moving. That's your reference point. Another 60 degrees, what's that? 180. Another 60 degrees, that's 180 plus 60, that's 240. Another 60 degrees, that's 300. And then I would call this a sixth rotation, but notice that's 360 degrees. We don't say 360 degrees for a number of degrees of rotation, so we just say that there are 5 different angles of rotation that's going to carry the shape onto itself. I'll write them out here. So even though the minimum degree of rotation is 60 degrees, all of these other measurements are also valid measurements of rotational symmetry. All right, got all that? Good. Let's take a look at the model problem. In this model problem, I drew a square on the coordinate axes. The first question is, what is the minimum degree of rotation required to carry the shape onto itself? Remember that formula from earlier. And also to write the equation of a line of symmetry for the shape. You can go ahead and pause the video and try this out, and then come back to see if you got it right. All right, first things first. We know that a square is a regular polygon with 4 sides, so n is equal to 4. So we can use the minimum degree of rotation formula, which is the angle is equal to 360 divided by n. N is equal to 4, so we substitute that in, and we get the angle is equal to 90 degrees. So we can rotate this shape 90 degrees around to carry the shape onto itself, or map onto itself. And it didn't ask, but if the question did ask, the center of rotation is 1, 1. It's right there. And we can tell that because it's in the center of the shape, right? It's the middle of the shapes there. So next, we're going to show the equation of a line of symmetry for this shape. And you can tell that this line, y is equal to 1, which is a horizontal line, that is a line of symmetry for this shape only because the top and the bottom are exactly the same. They're mirror images of each other. In other words, the top of this square is a reflection of the bottom of this square. But that's not the only line of symmetry for the shape. As a matter of fact, there are 4. Here's another one. And of course, this line is x is equal to 1 because it is a vertical line. And it's another line of symmetry because it splits the shape directly in half. In other words, it creates 2 mirror images of each other. But that is not the only line of symmetry. Here's another one. This should be a familiar line to you. This is y equals x, which is a diagonal line, and we can tell that it is a line of symmetry because it splits the shape in half. That top half and that bottom half, or I guess you could say the left half and the right half, are exactly equivalent to each other. There's one more line of symmetry, and here it is. And we call this line y equals negative x because the slope is going down 1 and over 1, and plus 2 because the y-intercept is 2. So we've established that this square has 4 different lines of symmetry, and if you recall from the notes previously, I showed you a picture of a square, and it does in fact have 4 lines of symmetry. It's easy to predict how many lines of symmetry a regular polygon is going to have because it's equal to the number of sides it has. For example, a regular pentagon has 5 sides. It's also got 5 lines of symmetry. 6 sides for a hexagon, and it's also got 6 lines of symmetry. That's a good thing to remember and keep in mind. The check for understanding you are going to be doing during class, so I'm not going to go over that, which means we've reached the end of the video. Again, this was a video on the Unit 4, which is Transformations Unit, Lesson 5, which is about rotational and line symmetry, making shapes map onto themselves. All right, folks, good luck studying.